And so we can say that orbitals are the allowed energies. Orbitals tell us, you know, the regions in space of having high or higher probability of finding the electron. What else can you say about orbitals? Oh. Think about it for a minute. Right now.
You should play that today. Oh. I know. No, I was on track.
No, I'm going to study.
All right, so does someone have some more things they can tell me about orbitals?
Sheldon?
Oh, no. All right. What else? From Google.
Oh, you want to know this?
Yeah, I want to know what they say.
Each of the actual or potential patterns of electron density that may be formed in an atom or molecule by one or more electrons, and that can be represented as a wave function.
Okay, is that it?
And then it goes into the origin.
All right, well, tell me about the origin.
Well, the origin of the word.
Okay. How about, well, you should be able to tell me more than that, right? What else do you know about orbitals?
It stays close to the nucleus. Sorry, that was electron.
The electron is going to stay close to the nucleus, yeah.
So
Each orbital has three quantum numbers.
Yeah, each orbital is defined by three. Where do those quantum numbers come from, N, L, and M?
Oh, from psi.
Well, psi is a function of N, L, and M. Actually, where does psi's come from?
Uncertainty principle.
Well, that's factored in. The uncertainty principle along with the other guy, de Broglie. And so the Heisenberg uncertainty principle and de Broglie and basic quantum or physics gave us the Schrödinger equation. The Schrödinger equation is the heart of quantum mechanics, and these orbitals come spit out by the Schrödinger equation as the answers to the question, you know, what's going on with the electrons in a hydrogen atom. And so there's other ways, you know, when somebody asks you what is an orbital, you know, some people might say an orbital contains all the information for an electron in the hydrogen atom. Well, what is all the information? All the information is, does it tell you the color of an electron?
No. The color, shape, or size.
Yeah, it's not going to tell you the color or the size of an electron. It will tell you the shape, but not the shape of an electron. It'll tell you the shape of the electron cloud. Now, what was the electron cloud? And so we looked at some electron clouds. You know, we looked at the psi 100, an electron cloud, you know, around the nucleus that we represent with dots. Each dot, maybe, you know, the electron's here at this point in time. It's here. You know, we can't really predict if the electron's here, it's hard to predict where the electron's going to be next. It's going to be within here with this probability. And the probability, it's going to be within here within what probability? Well, typically the probability that we talk about is the, did I say 90% probability, right? Well, it turned out, that's wrong. Sorry. It is the 95% probability boundary. And so we just put 95. That means there's a 5% probability that the electron can be found outside. Now, how big is the 95% probability boundary? Well, pretty small. Pretty small. And so the 1s, we call this the 1s orbital, or the 1s electron. The 1s electron is going to be around the nucleus with a 95% probability. And then we talked about the next allowed orbital. The next allowed orbital was the... Did we talk about the 2s? No? Very briefly. All right, so did I map out the 2s and 2p? 2, 0, 0, 2, 1, negative 1. We did that already? No, just the 2s. All right, the next allowed is if m equals 2, then L takes on two values. L can be 0 or L can be 1. But can L be 2?
No.
No, that's forbidden. And why is it forbidden? Yeah. Because the max is n minus 1. It's one of the restrictions. And if we don't follow the restrictions, then what happens is the wave function no longer becomes an answer to the Schrodinger equation. In fact, it turns out it's false. And so if L equals 0, then the m value ranges from plus 0 to minus 0, or just 0. If L equals 1, then the m value ranges from minus 1 to plus 1. Minus 1, 0, plus 1. And so over here, we get one orbital, because there's only one m value. And so this is the 1, 0, 0. Over here, we get three orbitals. We get the psi 1. Oops, this is 2. Sorry. 2, 0, 0. 2, 1, negative 1, the psi 2, 1, 0, and the psi 2, 1, 1. And so we see we have three different m values. Three different m values means three different orbitals. 3 m values equals 3 orbitals. And we're going to have 3 orientations for those. And it turns out these are what we call degenerate orbitals. Degenerate just means that these 3 orbitals share the same energy. Same energy. From the Schrodinger equation, we can figure out what the energy is. The Schrodinger equation gives us that the energy depends only on n, and that the energy is equal to minus r sub h over n squared. Do you remember this empirical formula from the Bohr model? Well, it's the same for quantum mechanics as it should be, because the empirical formula is just based on experimental fact. So it's the same. All right, now we have the energy. We can figure out the energy of these orbitals by plugging in n into this equation. And so we got the energy part. And what else do we want to know about the electron? We want to know its energy and its location. And its location is going to be given by the electron cloud. Electron cloud. The electron cloud is just this kind of dot thing, or there are other ways of representing this, you know. The other ways of representing the electron cloud would just be a hard sphere. This would be the 95% boundary. And so we call this the psi 100 or the 1s orbital. But is it a hard sphere? No. It's just a boundary in space, you know, imaginary boundary in space that we use to kind of get a handle on the size. Because if somebody asks you how big an orbital is, well, you could tell them the 95% boundary. It's one way. But all orbitals, did you know all orbitals are the same size? The reason all orbitals are the same size is because the probability doesn't drop to 0 until you're infinitely far away. And so if you were to look at the total size of the orbital, then all orbitals are infinitely big. But the probability of finding an electron, let's say 35 angstroms out from the nucleus, is so small that it's highly unlikely. And so what we have is we have a region of high probability, and then it drops close to 0. It stays 0, close to 0 all the way out to infinity. And so this is a much better representation of that. All right, so let's take a look at these individual orbitals here next. The 200 orbital. And so the energy of the 200 we calculate using this equation. And now we want to know about the position. And so typically what people do is they just kind of memorize this. The 200 is going to look similar to the 100, but one thing for sure is it's bigger. It's bigger because the electron has more energy. It's higher energy. And if it's higher energy, that means it can pull away farther from the nucleus. You know, it isn't subject to the nucleus's electrical pull, that attraction. And so the 2s is larger, like this. And there's one other feature with the 2s. It's spherical in shape, but there's a region here where there's 0 probability. There are no dots found. There's a gap, exactly. And then it drops down to 0. This region here, this is for the psi 200. This region here is called a node. Did I talk about nodes last time? And so did I draw the wave function for this? What would the wave function look like? For the 200, the wave function is, let's say the nucleus is right here. The wave function is going to have the highest density of dots right next to the nucleus. Here. Right next to the nucleus. And then that density of dots is going to decrease down and actually go through 0 and then look like this. So this is going to be symmetric. It's 1D plot, 2D plot. And so again, what we can do is we can draw the 95% boundary. The 95% boundary, we'll do it in green, it should be consistent with the colors. And let's say the 95% boundary is out here. And so one of the differences between a 1s orbital and a 2s orbital is the 2s orbital is a lot bigger when you look at the 95% boundary. It's got to be a lot bigger to contain 95% of the dots. So this would be the 95%. Now, that would correspond to 95% of the area under the curve, you know, here and here. Yeah. Okay, when we want to figure out the probability, is there such thing as a negative probability? No, the lowest probability you can have is 0, which means it's just not going to happen. And so what we do here is to get rid of the negative sign, we square the wave function. So psi squared is actually going to be the probability. And so if we square this, it's going to look like this, where the negative is now going to be positive. but we end up losing a bit of information about the wave function. What information do we lose? The sign. And so what is the sign of this one? This lobe, we call it. It's positive. And the sign or the phase of this? Negative. And so what your book does is it color codes this. So, when we look at the 200, we'll have a red inner, what we call lobe. And then outside of this, there's going to be a node. Outside of this, we're going to have a blue outer. Lobe. So this is going to tail off here. If we look at the 95% boundary, then we can contain the whole thing in here, like that. All right, so there's a node. We call this node a spherical node. It would just form a sphere in the center here, between the red and the blue region. This is a spherical node. And a spherical node is just a point where there's probability's gone to 0. All right, if we look at the psi 2-1 series, for example, psi 2-1 -1, psi 2-1 0, psi 2-1 1. This is called a subshell or sublevel. A subshell is a group of degenerate orbitals. And these degenerate orbitals are going to have all the same L value here. So when we look at these orbitals, let's take a look at the wave function here. The wave function might look something like this, where you have a wave, kind of looks like that. There's going to be some positive amplitude here, some negative amplitude here in the wave. This is our psi. And then if we look at our psi squared, psi squared, call this the 2-1-1. 1-0, maybe 1. In two dimensions, this is psi squared. What we notice is that in this orbital, there's a node right in the middle here. This would be a node. Usually this is the positive, this is the negative here. And so if we're to do the electron cloud for this, then we see, the most probable would be slightly, not at the nucleus, but slightly away from the nucleus on both sides. And so we can do that here. Just go ahead and do the electron cloud. Put the nucleus here. And then there's going to be a region of high probability, maybe at this distance away. We've got the most dots here. And then the probability drops as we get closer to the nucleus. And then as we get further from the nucleus, it also drops. So something like this. Okay, that's symmetric, so on both sides, see the same thing. Highest probability slightly off from the nucleus. Drops. And then there's dots out here. So if we look at the 95% boundary for something like this, it's going to look like this. Here, this would be the 95%. This type of node is a little different. This is called a planar node. You don't have to know the names, planar node or spherical node. I'm just telling you. But you should know what a node is. It's a planar node. All right, there are actually 3 of these orbitals, and the only difference is the axis that they're oriented on. So for example, if this one's oriented on the x-axis, then we'll have another one of these dumbbell shape on the y-axis, and then a third one along the z-axis, all orthogonal to each other. And so we can call those by different names. We call it, for example, if this is the 2px, then we have a 2py, and the 2py would just have a 95% confidence limit along the y-axis like this. It'd have 2 what we call lobes. The lobes, one above, one below. The 2s orbital also had 2 lobes, an inner sphere and then the outer. So this is 2py. And then the 2pz sticks out in the plane. And so we have one lobe coming out and one lobe going in, like this. Something like that. And so that would be the 2pz. And so we just name these. One of these is the psi 211. The other, I think this is the psi 210. I'm sure. This one was the psi 210. This one would be the psi 21 -1. Something like that. You don't have to know which one is which. I forgot because it's been a while since I did the calculation. And so just 3 different orientations, 3 different orbitals. The orbitals are exactly the same energy. Only difference is the orientation. Okay. So let's take a look at what we have so far. Some figures. I actually had a nice video on orbitals, but it's disappeared. This morning I was looking for it. Now we'll take a look at the figures from your book. So we'll talk briefly about, this is some of the math of wave functions. I told you these wave functions are actually algebraic expressions, and they break it up into 2 parts. There you put the variables, NL and in. Otherwise you'd see variables. You'd see one equation with 3 variables. And so they just pick the variables, This is the PX. And they put the N, L, and M, and then they come up with this equation and that equation. And the math you don't have to worry about, but the math is not terrible. At least for the hydrogen atom, it's not terrible. And this is just more, the same. I wish they showed the equation, the wave function like this, with N, L, and M in there. But that's okay, we don't need to know that. All right, this is the 100 orbital. I can tell because of the shape here, it's spherical. Do you see any nodes here? No, I just see positive amplitude here. This is the actual wave function in the 3D drawing. But you can see, the wave function, if we square this, we get the probability. Actually, this is the probability. This is the wave function squared. you can see that it rapidly drops off. And so there's minimal probability of finding electrons, let's say 35 picometers from the nucleus. Minimal probability. The greatest probability of finding the electrons within this region here. And the highest probability is going to be right at the nucleus. It's the highest probability because that's where the probability peaks, right there. Over here, they show different contours. This is a 95% contour here. And you can barely make out the dots. Do you see the dots? The dots represent the electron cloud. You might not be able to see it, but look at your book. You'll be able to see it more carefully. And so 95% of the dots are captured by this ring. 5% of the dots are outside. But that 5% is spread out from here to infinity. And so it's very low probability finding those dots from there to infinity. And so here, this is more, a more favorable representation of the size of the orbital. You wouldn't want to say that the orbital is infinite just because there's a minute possibility it could be out there. You'd say the orbital is about this size, according to the 95% boundary. Okay, so we see that. And so this is a 1s orbital. The 2s orbital obviously is going to be a lot bigger because the orbital is going to have more energy. In fact, the 1s orbital is in the hydrogen atoms, minus 2.179 times 10 to the minus 18 joules. The 2s orbital is going to be 1/4 that in terms of energy. So it's going to be higher in energy. It's going to be less negative, more positive. And so this is higher in energy. The electron can be further out. But an interesting thing happens here. Do you see it? There's a spherical node in there. And so here's where the wave function was positive and then it went negative. We square it and then we get the probabilities here. And so this is the 2s orbital. Here's the 3s orbital. The 3s orbital starts off positive, the wave function, then it goes negative, and then it goes positive again. And so you can see the 3s is going to have how many nodes? Where crosses the x? Two nodes. Okay, so the first thing is we start to see a pattern. Do you see the pattern?
Yeah.
The pattern has to do with the number of nodes. And so you see a pattern and then, okay, what do we do with patterns? We try to make a law. And so let's make a law of the nodes. And so what is your law of the nodes going to be? Is there a law governing the nodes, the number of nodes? Yes, right. And so that's the law of the nodes. How many nodes are you going to have? There's no such thing as the law of the nodes, but, essentially that's it. A lot of people memorize these because sometimes you get asked questions like, if n equals 99, let's say I'm looking at the 99s orbital, how many nodes are there in the 99s orbital? 98. And so 98 means you're going to have a lot of lobes because we got to start dicing up the cloud, right? Each time you add a node, you got to cut the cloud. And so we got a lot of lobes. Lobes are, this would be a lobe in here, and this would be another lobe here. But the law of the nodes is the number of nodes is equal to n minus 1. So if n is equal to 1, do we have any nodes? Internal nodes? No. N is equal to 2, we got 1 node. N equals 3, 2 nodes. N equals 4, 3 nodes. And that's a consistent pattern. So a consistent pattern is called a law. So that's the law. All right, let's continue on. This is the 3s. And so here. Actually, let's look at some more. What is this? Orbital here. If you look at this, that looks like the P py orbital. If you call this the x and this the y, this looks like the py orbital, right? Or the 2, 1, whatever, 2, 1 something orbital. What's that? This is another representation. This is the 2p. Well, this says they're saying is the z-axis here. So we would call this the 2p z orbital, or the psi 2 1. I forgot what I called it. 210, I think. That's what I called it. Did I? The psi 210. And so we see here's psi squared. So we see a peak here and a peak here. One of the peaks comes from the positive amplitude. The other peak comes from the negative amplitude. And so one of these is positive, one of these is negative. Here you can see where the peak in probability is. The highest probability is here and here. We did the electron cloud. This is a contour diagram showing kind of the shape, three-dimensional shape. If we, and I'm not going to have you do any contour diagrams. I'm not going to do those. Instead, we're going to just draw it like this. Here's the PZ. Just take that, rotate it so the z-axis is vertical. Here's the positive amplitude part. Here's the negative amplitude part. Red and blue. But this is one orbital. It's one orbital that's been sliced here because of this node. And so we have two lobes here. See that? Two lobes. Is there a law of the lobes? How many lobes do we have? It looks like we have n lobes, doesn't it?
Yes.
And so maybe that's the law of the lobes. We can figure out how many lobes, that is, you know, what do we slice the electron cloud? How many pieces do we slice the electron cloud into, you know, because of these nodes? This is one orbital with two lobes. This is, you know what, this is an n equals 3. In n equals 3, how many nodes do we have? N equals 3, we're going to have two nodes, right? Two nodes. And so if I take the electron cloud, I slice it here, that's one node. That's called a planar node. Did I talk about planar nodes? It's a planar node here. And then I slice it here, it's another planar node. And so n equals 3 is going to give me how many lobes? I count 1, 2, 3, 4 lobes in this one. It's like a clover leaf. Yeah. 4 lobes. But I saw another n equals 3 orbital. Here's another n equals 3 orbital. N equals 3. Hey, wait a minute. Didn't we say that there are going to be n lobes? N lobes? So n equals 3 gives me 3 lobes. 1, 2, 3. N equals 2 gave me 2 lobes. 1, 2. I'm telling you, these are n equals 3, but I have 4 lobes. So what does that tell me about the law of the nodes? There's no law of the lobes. There's no law of the lobes. But there is a law of the nodes because this is consistent. I'm not going to find any violations. Okay? And so we don't have an equivalent law of the lobes because it's not consistent. And so let's look at the n equals 3 for right now and see what we got here. So what are these orbitals here? Well, let's take a look at the allowed states of the electron when n equals 3. What are the allowed states? Well, when n is equal to 3, L can be 0. If L is 0, then M goes from plus 0 to minus 0, so M is 0. And so the allowed state is psi 300. What does a psi 300 look like? We saw it over there. It looks like a 3s orbital because that's what it is. It's a 3s orbital. So we're going to have an internal, and then a middle, and then an outer. And so they're going to be how many nodes? 2 nodes. And so I can draw maybe with dots, might be better. And so the highest probability is going to be right at the nucleus. Interestingly enough, all these, the 2s, the 1s, and the 3s all have the highest probability right at the nucleus. The only difference is a 1s is the probability drops off rapidly as we go out. The 2s, it spreads out further, and the 3s spreads out even further. And so even though there could be overlap in the position, like a 1s orbital can be found in the same exact region of space as a 3s electron or orbital, when we look at the cloud as a whole, it's different. And so we got this one node here, and then another node here, and then this is going to tail off to infinity. Here. And so probably the easiest representation of this is just to look at the 95%. The 95% boundary for the 3s is going to be bigger. And so this might be the 3s 95%, a 2s 95%, and a 1s 95%. So the 1s is going to be much, much more smaller. 2s is bigger, the 3s is bigger in terms of the 95% boundary. And so it's just a bigger sphere. All right, then we go to L. The next allowed set of L values will be L equals 1. So we have L equals 0, L equals 1. If L equals 1, then the allowed M values are from minus 1 to plus 1. In other words, minus L to plus L. And so we generate 3. Psi 3, 1, negative 1, psi 3, 1, 0, psi 3, 1, 1. Let's pick one. Let's pick the 3pz. I think I called it this one, so we'll go with that, 3pz. The 3pz is going to have a cloud distribution that looks like this. We're going to see some probability here along the z-axis, like this, and down here, above and below the nucleus. And then there's going to be a node. The type of node we have is like this in the S. It's a spherical node. So this will be a spherical node. And then we have some probability out here. And so what it looks like, it has the dumbbell shape of p orbitals, except there's a node slicing the cloud here and down here. And so we have multiple lobes here. In fact, we have 4 lobes here, or 3 lobes here. And so it looks like a 2p, but we got this spherical node, which is slicing it, and it's much bigger than a 2p. A 2p orbital is going to be quite a bit smaller. Okay. We looked at the 95%, it's bigger. 2p is smaller. So this will be a 3p. And the others would look exactly the same. They're just oriented on the x and the y-axis instead. That's it.
Where's the other node?
The other node is here. The planar node. And so like the 2p, the 2p just had one planar node. But now the 3p is going to have one planar node and one spherical node. So it's going to slice it like that. All right, so we call this the S sublevel, or subshell. This is called the P subshell. And then we have one more to this. And so let me erase this here. Write it. When n equals 3, we can also have the L equals 2 value. If L equals 2, then M can range from -2 to +2. So we go -2, -1, 0, 1, 2. And so here we get 5. 5 M values means 5 M values mean how many orbitals? Five orbitals. In fact, do you see a pattern? Do you know the pattern? The number of orbitals in a subshell, we'll call it the law of the number of orbitals in a subshell. Okay. What is the law of the number of orbitals in a subshell? How many M values there are? Yeah, that's one way, but there's a simpler way of expressing it. Law of number of orbitals in a subshell. The number of orbitals is equal to maybe we need to do more. Maybe you need to do more observations, or do you have enough observations to figure it out? Try to figure it out from the number of observations that we've taken. Do you see a pattern? A mathematical pattern, because the laws are just a mathematical equation that fit the pattern. M plus L? N plus L. And so N is 3, L is 2. Oh, that works. 3 and 2 is 5. Okay, let's try it in the 3P. In the 3P, N is 3, L is 1. And so that's 4. 3 and 1. And did we have 4 orbitals? No. And so if the law doesn't fit the factual data, then it's no good. We don't want too many laws where we have to memorize exceptions. Don't you hate that? Oh, this law works for this, but it doesn't work for what we just did previously. Do you like those exceptions? Everybody hates those exceptions, right? But that's a lot of ways. That's how it's taught. You know, you got to memorize all the exceptions. This law works except for
L times 2 plus 1.
yeah. The number is equal to 2L plus 1. That seems to work for all of them, because if L's 0, then we only had 1 orbital. If L's 2, then we had, well, 5 orbitals. So 2 times 2 is 4, plus 1 is 5. If L's 1, we have 3 orbitals. So 2 times 1 is 2, plus 1 is 3. So far it works. So what we need to do with our law is test it and see, will it hold? And so we'll try it and see if we can continue using it. And so anyway, we have 5 orbitals. What are the orbitals? We're going to have the psi 3, 2, minus 2, the psi 3, 2, minus 1, the psi 3, 2, 0, psi 3, 2, 1, psi 3, 2, 2, and psi 3, 2, oops. I screwed it up. Minus 2, minus 1, 0, plus 1, plus 2. I didn't screw it up. I got too many orbitals. I should only have 5 orbitals. And so what do these 5 orbitals look like? They look like these 5 orbitals here. And so these are the psi 3, 2, and each one of these M's has a different designation. So for example, -2, and you have to do the calculation because they didn't correlate it here. But we have this, the geometric designation versus the number designation. And so -2 corresponds to one of these. And the way they're named is you can either call it, the psi 3, 2, -2, or you can give it the d, the 3d. This is the 3d x squared minus y squared. Now, x squared minus y squared means that the lobes are going to be right on the xy axes. This one's called the 3dxy, and that corresponds to one of these here. And the 3dxy has the lobes between the xy axes. And then we have the 3dxz. We look at the xz plane and put the lobes between the axis in the xz plane. The 3dyz is the yz plane with the lobes between. All these have how many nodes?
4.
Nodes. They have 4 lobes, but how many nodes? 2 nodes, 2 planar nodes, here and here, right? Splits it into 4 lobes. But here we can see the violation of the lobes because, well, actually, no, this doesn't quite violate. This violates it because this purple is supposed to be a donut ring around here. So there's a donut ring that circles this. And so this would be like a p orbital with a hula hoop, but in terms of shape. And so this only has 3 lobes. And so these all have 4 lobes. This only has 3 lobes. 1 up here, 1 hula hoop, and 1 down here. It's 3 lobes. And so there isn't a consistent pattern with the lobes. But there is a consistent pattern with the nodes. So what kind of nodes are there? How am I going to slice this? If there's a hula hoop here, how can I slice it like this? Or slice it like that? Where are my nodes when I got this hula hoop ring around here? Can you see?
A cone shape?
Yes, exactly. You got it. It's a cone-shaped node. This is called a conical node. We have 2 conical nodes, one going up, one going down. So conical nodes, exactly. And so that's how we get 3 lobes there. But all these are degenerate, meaning even this one with the hula hoop is going to have the same energy as all the others. And so these 5 orbitals have the same energy, just different, what do we say? They have the same energy, but just different orientation. So that's the D. All right, let's continue on. Yeah. So when n is equal to 3, can I have L equal 3? No, that violates. And so the next set of orbitals will be the n equals, well, I can't do n equals 3. I have to go jump up to n equals 4. Now take a look. I want to know how many orbitals am I going to be dealing with in the n equals 4? We call it the n equals 4 shell. Shell. In the n equals 4 shell, how many orbitals are there? See if we could have come up with a new law. The law of the number of orbitals for a given n.
L plus 2.
So this is the law of the number of orbitals total for a given n.
Minus 1 times 2 plus 1
n minus 1 plus 2.
times 2
n
plus
minus 1. n minus 1 times 2
plus 1.
plus 1. Okay, so if n equals 0, well, actually 0 is not possible. Is 0 possible? No, n equals 1. So in n equals 1, we saw one orbital, the 1s orbital. Does this law hold?
No.
N minus, so 1 minus 1 is 0 times 2, that holds. And so n equals 2. N equals 2, how many total orbitals did we see? We saw 1s and 3 2p's for a total of 4 orbitals. And so that would be 2 minus 1 is 1 times 2 is 2 plus 1 is 3. Sorry. It's not valid. Huh?
N squared.
N squared? Let's try. So if n equals 1, we get 1 squared. That gives me 1 orbital. If n equals 2, it's 2 squared, a total of 4 orbitals. That's correct because we had a 1s and 2s and 3 2p's. So that's right. N equals 3. N equals 3, we have 3 squared, which means 9. Did we have 9 orbitals? Yeah, we had a 3p, 3 of those 3p's, 1 3s, and 5 3d's makes 9 total orbitals. And so when we get to n equals 4, how many orbitals am I expecting? 16. And so what are they? Well, that's the great thing about quantum mechanics. You know, we can figure all these things out by a simple set of mathematical rules. And we can figure out all the orbitals from n equals 1 to n equals infinity. So for example, when I get to n equals 100, how many orbitals are there in n equals 100 shell? A lot, 100 squared, right? And so, well, what are they? Well, we can figure those out. I'm not going to ask you on a test to figure all those out, but I might ask you something harder than n equals 4 because that's only 16 orbitals. 16 orbitals is not that hard to generate. And so let's go to, oh, actually, before we go to that, let's take a look at this. What orbital is this? It looks like a p orbital, doesn't it? It looks like a p orbital, but do you see what is this here? A spherical node. How many nodes are there? 1 node. So this must be a...
Isn't there 2 nodes?
Oh, actually 2 nodes. There's a spherical node and a planar node. So 2 nodes. So that means this must be a... three p, and it's along the z-axis, so this is a 3pz orbital. Do you see that? If you look at this, this looks like the clover leaf, 4 lobes, right? So it looks like what kind of orbital? You're good at it. How did you figure out it's a 4 without, if this was blanked out, I should have done that. But if you didn't know it was a 4, how could you figure out what n is? N's easy because we know the law of the nodes. The law of the nodes says that, well, we got how many nodes here? We got 1 planar node here, another planar node here, and a spherical node here, which gives me 3 nodes, so that must mean it's a 4D. And this one, it's in the xy plane, so it's 4D xy, and it's between. If the lobes were on the axis, we call it dx squared minus y squared. You don't have to memorize these designations. Okay. But this orbital corresponds to one of the psi 4. You know what it is? It's a psi 4, 2, either the -2, -1, 0, 1, or 2. Okay, that's what it corresponds to. Let's move on. Almost done for today.
Professor, why is it 4-2?
Okay, I'll talk about that right now. There's another pattern here that you can either figure out or you can memorize. Let's talk about that next. And that's a letter designation. And so the way we typically map out these allowed energies is we come up with a diagram like this. Do you know what this diagram is called here? Ignore this one on the right here. We're not going to talk about this one yet. But just this for the hydrogen atom, this is the energy level diagram. Energy level diagram. When n equals 1, we have how many orbitals? 1. When n equals 2, we have? No. We have 2 sublevels, right? Remember the law of the sublevels? We have 2 sublevels for a total of 4 orbitals, n squared orbitals. We have n sublevels, n squared orbitals. Each sublevel will have 2l plus 1 orbitals. And so here's where the s comes in. And this is L. When L equals 0, we call it an s orbital. When L equals 1, we call it a p orbital. L equals 2, we call it a d. L equals 3, an f. L equals 4, what do we call an L equals 4?
G.
G, you're right. We call it a G orbital. L equals 5, we call it a H orbital. What do you think the pattern is? What comes after H? I. And it goes alphabetical. And so why didn't it go alphabetical right at the beginning? Why didn't we just start with A, B, C, D, right? And so some people say, well, S. What was the shape of an S, 1s orbital? Spherical. 2s orbital, spherical. 3s orbital, spherical. And so a lot of people think of S. The easy way to remember S is spherical, but does S stand for spherical? Because if S stands for spherical, then what was the shape of a p orbital? It was dumbbell, or figure 8. And how do you get a dumbbell or figure 8 out of p? D was that 4-leaf clover or the hula hoop p orbital, right? And so what's going on with those? And so what's going on with these is this. The origin of this is from, the origin of these letters is from spectroscopy.
So what happens when you get to S? You just put A.
X, then double A, whatever, just some pattern. So the origin is spectroscopy because origin spectroscopy because when they were looking at the spectrum of a lot of these atoms, they noticed that some of the lines were sharp. S stands for sharp. a sharp line or a sharp peak in the spectrum. P stands for the principal peak in the spectrum. Principal, usually the biggest peak in the spectrum. You know? D stands for a diffuse peak in the spectrum. A diffuse peak is kind of a weak peak that's spread out over a pretty broad range of wavelengths. Something like that. And so SPD have spectral origins. The rest is just alphabetical. And so when you hit X, you would think you'd go back to A, but you probably don't go back to A because it's mixed up. But I'm not going to make you derive it that far. We'll just go here. You know, the energies here are going to be this. It's going to be minus R sub h over 1 squared, which is just minus R sub h. The energy of this is minus R sub h over 2 squared, or 4. This is going to have an energy minus R sub h over 9. The 4, and how many orbitals in the 4? 16, so I've got to go on more. But those are going to have an energy of minus R sub h over 16. And then this is n equals 4. And then we go to n equals 5. N equals 5 is going to have how many orbitals? 25. And the energy is going to be minus R sub h over 25. Now, the energies, you can see the biggest gap is going to be here. You know, we're going from R sub h, so it's three quarters. And then here, the gap gets smaller, and the gap gets smaller, and the gap gets smaller between subsequent levels as the fraction grows smaller. Do you see that? And then we go all the way up to n equals infinity. At n equals infinity, we got 0 joules. So we're going from minus 2.179 times 10 to the minus 18 joules to 0 joules, which, and n equals infinity, there's going to be infinity squared orbitals, which is huge, but all those orbitals will be degenerate. They'll all have the same energy. Excuse me. So the first thing we're going to do is we're going to do something like this. How many orbitals are there in the, well, let me see, 5H. N equals 5, L equals 5. How many orbitals are there in the 5H? 5H. And so this is called the 5H subshell or sublevel. And so in the 5H subshell, how many orbitals are there? This is a trick question. 11? It would be, well, H is 5, so we get 2L plus 1. You're right, it'd be 11, but it's a trick question. It's a quick trick question because how many orbitals are there in the 5H? 0. Why 0? Yeah. Because the maximum for 5, n equals 5, is G. The 5G is the max. You can't go to 5H because that would violate the n-1 rule, or the n-1 law. The maximum L value is 4. And so these don't exist. And so 0 is the answer. None. But what about 6H? How many orbitals are in the 6H? Then you're right. 6H would have 11 orbitals. And what are they? We could figure them out. And so this way, you know, it's not difficult to figure out. All 25 of these. I mean, it's not that many. And so let's figure out all 25 of these orbitals right now. And it doesn't take very long. Let's do that. Let's do that here since I'm running out of space. So I'm going to move that up here. And so what are they? They're the 5, That's my N. And the L, the first L value can be 0. 0. There's a 5, 0, 0 orbital. Right? That's the first one. This we call the 5s orbital. Then comes what? 5, 1, minus 1, 5, 1, 0, 5, 1, 1. These are the 5p orbitals. We're going to have the px, py, and pz. How many nodes in these p orbitals here? How many nodes? If I had a 5p orbital, how many nodes are there in a 5p orbital? 4. And so these are going to have a lot of lobes because it's going to be sliced and diced to make more lobes. And then I get the 5, 2, minus 2, 5, 2, minus 1, 5, 2, 0, 5, 2, 1, 5, 2, 2. These are my 5d orbitals. There's 5 5d orbitals, right? 5 5d orbitals. And then I go to 5, 3, minus 3, 5, 3, minus 2, 5, 3, minus 1, 5, 3, 0, 5, 3, 1, 5, 3, 2, 5, 3, 3. What do I call these? When L is equal to 3, then these are f orbitals. And so these are my 5f orbitals. How many 5f orbitals do I have? 7. You know, because it's going to be 2L, so that's 6 plus 1, 7 orbitals. It's 7 orbitals here. Okay, and so in the n equals 5 shell, so far I have 1 subshell, 2 subshells, 3 subshells, 4 subshells. I need 5 subshells, right? So I got 1 more subshell to go. And what is that subshell? Yeah, and so I'm running out of space here. Let's see, is this? Well, maybe I can, let's continue it down here. So what does it start off with? 5,
5, 4, negative
5, 4, negative 4, 5, 4, negative 3, 5, 4, negative 2, 5, 4, negative 1, 5, 4, 0, 5, 4, 1, 5, 4, 2, 5, 4, 3, 5, 4, 4. And so how many orbitals do I have? 9. In the 5G subshell, I have 9 orbitals. Let's go to 5H. How many orbitals in the 5H? Huh? 5H? None. And so this is where I stop. How many orbitals did I just make? Total? 25. Right? And so we have them all. We didn't miss any. We got all 25. All right. Now, all 25 orbitals, interestingly, have the exact same energy. These are degenerate orbitals. And so when we're looking at the hydrogen atom spectrum, this is what was happening. In the hydrogen atom spectrum, the red line was an electron being promoted up here. And so we have an electron up here in the n equals 3, and it drops down to the n equals 2. And we get a red photon being emitted. Red. A little higher in energy than that is if we go to the n equals 4. In the n equals 4, I have 16 orbitals. And so if an electron gets in the n equals 4 and drops down to the n equals 2, then I emit a green photon. And then I can go up to the n equals 5. The n equals 5 is going to emit a... So the electron's up here in one of these 25 orbitals. So there's an electron up here. It drops back down to the second and it's going to emit the blue. And then when I go to n equals 6, how many orbitals are there in n equals 6? 36. And so an electron's up here in one of these 36 orbitals up here. You know, it can be in any one of those. And then it drops down to the n equals 2, and I emit the violet. And so that accounts for the 4 visible lines in the spectrum. Now, there's additional rules. Because L is called the angular momentum quantum number. And in physics, there's something called conservation of angular momentum. So some transitions are forbidden. Like, I can't go from this angular momentum and all of a sudden go to that angular momentum. There's some kind of conservation rules, which means some of these transitions between orbitals is actually forbidden. And so, you know, some are allowed. But we're going to ignore that. We're just going to say that a bunch of orbitals here, the electron's in one of those, and it drops back down here. And so, in a way, it's similar to the Bohr. You know, the Bohr model had these energy levels like this, except there was only one state, and that one state was the orbit, the spherical orbit. Here, in the quantum mechanical model, we know, well, if it's got this energy, then we have this electron cloud, and the 2s electron cloud and the 2p electron cloud, so the electron's going to be occupying one of those. Now, comes the question, comes about why, you know, the 2s and the 2p have totally different shapes. The 3s, the 3p, and 3d have totally different shapes of the probability distribution. Why are these the same energy? Shouldn't they be different energies? Like this? You see these are different energies, the 2s and the 2p? These are not energetically degenerate. All the 2p orbitals are energetically degenerate, but the 2s and the 2p are not. And so over here, why are these the same energy? And so that's a question we have to answer first. To answer that question, let's go back and look at the 2s and the 2p orbitals in more detail. All right, this is one orbital here. These three are the same. You have to memorize the S and the P, the shapes. What orbital is that? This is a p orbital because it's got the two lobes like this. And this would be a 2p, 3p, 4p, 2p, because there's just one. No. And so this is the 2p orbital. When we look at the 2p orbital, we see this. Here, these surfaces tell us the 95% boundary, but they don't really tell us, you know, how the probability changes within that. We'd have to look at these maps to see that. Either what we call the contour map here that shows the peak here and the peak here, or the dots. The dots are hard to see here. But where is the highest probability of finding the electron? The highest probability of finding an electron is here or here. Both of these have equal height, therefore equal probability. So the highest probability is right here. You know, the nucleus is here, so it's right here or right here. It's the highest probability. So we can see it over here and here. And so let's take a look at the map for that. That looks like. But okay, let's go back to the past. Where's the highest probability of finding the electron in the 2s orbital? If I look at the highest probability, then I need to know what the wave function of the psi squared looks like. When I do psi squared of this, do you know what it looks like? Looks like this. And so where's the highest probability? The highest probability is right at the nucleus, right in the center. And so the highest probability is here. Here. You can't be right in the nucleus, but it's right at the nucleus, right? Where's the highest probability for finding the p electron? The highest probability is it at the nucleus? No, it's away from the nucleus. So if the nucleus is here, then the highest probability is here and here. How can these two have the same energy? Right? Because this one has the highest probability right next to the nucleus. And so the electron and the nucleus are right there together. This one, you have to pull the electron away from the nucleus. If you got to pull the electron away from the nucleus, you know what that does? That increases the energy. And so here we pull the electron away, it's increasing the energy, so how can these two have the same energy? One, the electron's right next to the nucleus, it's happy because the positive nucleus and the negative electron are right there. This one, the electron and the nucleus are kind of separated. It costs energy to pull the electron away from the nucleus, right? And so it doesn't make sense that they have the same energy. And so how can they have the same energy? Because they have totally different probability distributions. And so let's take a look at that just for a moment. And so if I look at the 2s orbital and I look at the electron cloud for 2s orbital, the electron cloud is the electron is going to have the highest probability right next to the electron, right next to the nucleus, and then drop off. I'm going to try to finish this quickly and drop off. And so when I look at the density of dots, the greatest density of dots, or the thickest part of the cloud, is right at the nucleus. When I look at a 2p, then it's away from the nucleus. It's over here and over here. Even though the cloud distribution is different, even though these two cloud distributions are different, they both have the same effective distance between the electron and nucleus. Now, what do I mean by the effective distance? Okay, when I talk about the effective distance, we need to, if they both have the same effective distance, then they both have the same energy. And so to understand effective distance, I got to talk about one thing. We know where the highest probability is. And so A, highest probability is simple. Highest probability equals max psi squared, where the top of the peak is. It's the highest probability. But we also have to know B, the most probable distance. The electron is away from the nucleus. And so when I look at this, the highest probability is right at the nucleus. So is the most probable distance that the electron in a 2s orbital will be is right at the nucleus? You would think so, but it's not. It's not, because the way we have to visualize this is like this. What we do here is we divide the space around the nucleus into like onion rings. You know, hollowed out spheres like this. And then we say the most probable distance will be the sphere. You know, each sphere is going to be a distance away from the nucleus. It's going to be the sphere with the most dots in it. Well, you say the sphere with the most dots should be the first sphere, right? Concentric sphere. But the first sphere is very, very small. So even though there are a lot of dots here, the volume of the sphere is so small, it doesn't capture the greatest number of dots. In fact, a sphere out here would catch more dots because it's bigger in volume. And so even though the density of dots isn't as great, because of the volume of it, we'll count more dots. A sphere way out here has a huge volume, but no dots. And so the most probable distance the electron is away from the nucleus, we have to maximize two things. We need to maximize psi squared and volume of these hollowed out spheres, these concentric rings. And so we got to maximize that. Well, psi squared, we know what that looks like. Psi squared for 2s looks like this. So the max is right at the nucleus. But what happens with the volume of each successive ring? It grows bigger. And so when we look at the volume looks like this. This would be the volume. This would be psi squared. And we end up with this. To maximize both, it's going to look like this. This is the max of both. And so we see we want the biggest volume with the highest probability. This max of both, the peak of this is called the most probable distance. The most probable distance. And actually, this is for, shoot, the psi squared is gonna have another hump because it's got this thing too. The most probable distance. This red curve is called the RDF, aka RPF, aka RPD. RDF stands for radial distribution function. Radial distribution function. RPF stands for radial probability function. RPD stands for radial probability distribution. all mean the same thing. So let me finish with this here. This is the hydrogen atom. If we look at the hydrogen atom, where's the highest probability of finding the electron? Right at the nucleus. But which one of these rings will have the greatest number of dots? Will it be the first ring? No. The most outer, maybe, maybe not. We got to maximize the density. In other words, we just count the dots. And it turns out, let's say it's this ring here. And when we look at the distance of that ring, do you know what it is? Do you know where the RDF maxes out at? Let me tell you. It maxes out at 53 picometers. 53 picometers or 0.53 angstroms. Have you heard that number before? Yeah, you might have heard that number before because that is the radius of the first Bohr orbit. The first Bohr orbit has a radius equal to A naught. What is A naught? A naught is 53 picometers. And so this is why Bohr got a radius of that, because that makes sense. That's the energy. Because the most probable distance is what we call the effective distance. If we could just fix the electron in one position, because sometimes the electron is very close to the nucleus, sometimes it's very far. But if we just fix it in one position that averages out all those fluctuations in distance, we would get the effective distance or the peak and the RDF. And that corresponds to 53. The thing with Bohr is Bohr said it's stuck there. Is it stuck? Is the electron stuck at 53? No. We know it can be close. We know it can be far because it's going to be in an orbital, not an orbit. But still, it's interesting to see that the RDF, the most probable distance, is 53, just like the Bohr, the first Bohr orbit. Now, what is the, that's for the 1s orbital. But what about the 2s orbital? Do you know what the effective distance for 2s orbital is? It's n squared r. In other words, it's 4 times. And so that means all the n equals 2 orbitals will have the same effective distance. Okay, and so we'll stop there and talk about the 2s and the 2p in more detail next time. So we'll stop here. We're going to meet over in the computer lab next. And we're going to work up the data together. Unfortunately, what does the note say on the stop time?